All right. Well, it's the day before Thanksgiving holiday, so let's see if we can move along here so we can get to the good turkey. Now, hope you all have great holiday plans. Okay, so now we're doing a theory of sets. We're applying propositional and predicate calculus to a theory of sets. So we're actually moving beyond the logic and we're into applying the logic. And by the way, this is applying the logic this way is something it's unique to this book. There's not very many books that treat discrete math quite this way, using logic as a formal tool. And so we've discussed 11.2, the relationship between set enumeration and set comprehension. And we've proved a few theorems about that. And then 11.3 is the definition of that operator an element of. And then 11.4 is the definition of what it means for two sets to be equal, right? So two sets are equal if and only if for all x range true x is an element of S equals x is an element of T. And then we did a few special sets, the empty set, the universe, and the singleton, the one with one element. And 11.5 is an interesting theorem. It says S, the set S equals the set over X, range X is an element of S, body X. Now, that little theorem is an interesting one, and it may seem obvious, but what we're going to do now is really kind of crucial for what we're going to be doing a lot in the future. We're going to prove 11.5, but to prove 11.5, we are going to introduce a proof technique, okay? And this proof technique that we're going to use it over and over and over again. So this is a pretty crucial proof that we're going to do here. So here's what we're going to do. Let's prove 11.5. So here, 11.5. Is this marker dark enough for the video? No, this one's better. Okay, so here's 11.5 and 11.5 proof. Now, let me ask you a question. Okay. Here we have on our slide here a theory of sets, and we're wanting to prove 11.5. So now let's always think about types, okay? If you always think about types, that's the key to understanding how all this stuff works. So what is 11.5 saying? It's saying that two things are equal, right?
Sure.
Now what is the type of the thing on the left?
Type set.
It's a set. And obviously what has to be the thing on the right?
Set.
It's a set. So what is this thing asking us to prove? That two what? Two sets are equal.
Okay.
So is everybody with me? That's it. So but how do we prove that two sets are equal? There's yes, extensionality 11.4. That's the thing that we go back to prove that two sets are equal, right? Are you with me? So to prove two sets are equal.
How's this rocket science?
How is this rocket science? It's all very common sense. I mean, to prove two sets are equal.
This is just for set.
What we use the definition of equality. Use the definition of set equality. Of set equality, which is 11.4. Okay, extensionality. All right. Now, but here's the thing. I'm going to prove 11.4 in 2 steps. We're going to prove 11.4 in 2 steps. Now, you guys remember that I think before we did
11.4. 11.4 is an axiom. You ain't gonna do it.
Sorry. I'm going to prove. Yeah, we're going to prove 11.5 using 11.4. Right. Okay. Now, do you guys remember that time when we were going through a proof and we said da 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 da. This equals this. This equals this for this reason. Da da da. And then we had a hint and we said lemma.
Yeah.
Blah 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 blah. And then we just kept going and boom boom boom. And then we said, okay, that's the proof. But we used a lemma. And what was the definition of what did we say a lemma was?
Small theory used to prove another theorem.
A small, yeah, it's a small theorem used in the proof of another theorem, right?
Okay.
Okay. So now, and then what we had to do to complete the proof is we had to prove the lemma, right? Okay, what we're going to do this time is we're going to prove the lemma first.
Okay.
Are you with me?
Yeah. I'm with you.
Okay. We're going to prove the lemma first. And furthermore, the lemma that we are going to prove, now check this out. You need to look, we need to look at this. This is a crucial slide here. Let's go back to 9.8. 9.8 says, and this doesn't have anything to do with set. 9.8 doesn't have anything to do about sets, right?
Nope.
What it says is that for all x, range R, body true, that equivals true. Did you prove that in a homework assignment? 9.8?
Prove that.
Do you remember 9.8? Or maybe you did the
Yeah, we
exists.
proved it. We proved that. Remember, because I struggled.
I think it's true and true and true.
Well, yeah, but that's not why you do it. Yeah, you proved it. Okay. But anyway, okay, so what we are going to do is we are going to, as it turns out, 9.8, it's 9.8 is the key to using 11.4. 9.8 is the key to using 11.4. What? Okay, and here's how it's going to pan out. Oh, actually, maybe let me just jot that down, okay? So the proof is based on, the proof is based on 11.4 and 9.8. And 9.8 is for all x, range R, body true, equivals true. Okay, so if you'll bear with me now, what we're going to do is we're going to start with this time we're going to prove the lemma first instead of, okay? So it's in 2 parts. Okay, so here's part 1. So proof of 11.5, part 1. Are you with me?
Where part 1 is the lemma.
And part 1 is going to be the lemma. And what we're going to do is we're going to prove what we call the 9.8 lemma. Prove the 9.8 lemma. We're going to call it the 9.8 lemma. That's going to be our terminology. Okay, we're going to prove the 9.8 lemma. Now, this next sentence that I'm going to write down is the way to do this. You'll do this. So if you prove the 9.8 lemma, start this way. It's an English sentence. We say let V be an arbitrary element. All right?
Like potassium?
Or iron or gold or okay, so let V be, no, by element we mean an element in a set. An element of a set. Okay? And here's what we're going to do. We are going to show, let V be an arbitrary element. Here, let's make this a comma. And show that V is an element of S equivalence V is an element of the set X, range X is an element of S, body X. Are you with me? So what, is everybody clear what this step is? What this step is, because what we want to prove is that, let's move on back to, is that S equals this set. So what we're going to do is we're going to say, okay, let's let V be an arbitrary element, and let's prove that V is an element of S equals, not us, no, it would be equivalence, because S equals this, that's equality between two sets, but V is an element of S is a Boolean, right? Equivalence, V is an element of this. So V is an element of S, equivalence, V is an element of this. Are you with me? Okay. So now, how do we prove these two things? Well, let's get one side equal to another side. And which side should we obviously start with? Let's start with the right side because it's more complicated. See if we can get that to be this. Are you with me? Okay, so we'll start like this. We'll say V is an element of the set X, range X is an element of S, body X. Okay, who wants to go first? It's pretty obvious what you have to do here.
Okay, wise guy. 11.3.
I think 11.3 is great because after all, it's V is an element of something. 11.3 says, does the definition of F is an element of something, right?
Sure.
And furthermore, it's an element of this, yeah, of this. Okay, so this, great, call 11.3. Okay, so 11.3. So now, Ben, you want to go next? So what does 11.3 say? It says
there exists in X.
there exists an X.
Range X is an element of S.
X is an element of S.
Body
Body,
V equals X.
yes. Now, are we good? Is everybody with me on that? Is everybody with Ben on that, right? We're just using 11.3. It's da-da-da, F equals E, so V, yeah? Are we good? Okay, well now what? Anybody have any ideas now? How can we
Trading. 1 point rule.
oh, that was a good,
Yeah, trading.
okay, so now, so how,
What double trading is?
yeah, well, what,
Double trading with exists. And then
yeah, so, okay, so this equals by, now, so what are you saying? How can we swap these?
existential double trading.
Existential double trading.
Yeah.
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 And what is that? So existential,
Exchange.
Existential.
Body.
Nice.
double trading. And which number is that?
I don't know.
It's 9.20.1.
10.20.1. 9.20. Oh, we didn't. 9.20.1? And that gives us, Rochelle, what does that give us?
It gives range equals X.
Body.
X. How do you say that?
X is an element of S.
X.
Okay? So X is an element of S. That's how you say that. Okay, and notice that we're not doing sets here. This is an existential quantification. And now what pops out at you, Kyle?
1 point rule.
1 point rule. And what number is that?
9.1. That was a guess.
That was a guess.
814 for 1 point rule.
8.14.
8.14. 9.1, 8.14, what's the difference?
1 point rule.
Close.
Call it that.
And how do we do, what do we do with 1 point rule? How does the 1 point rule work? You take what?
The body.
You take this, okay, so you take x is an element of S.
And textual substitute X. With the-
Yeah, and now the quantified variable is x.
Right.
So is this x replaced by v or v replaced by x?
You replaced by X. X replaced by X.
Well, you better look up 8.14, huh?
Is right, extra plus by B.
X replaced by
Extra
V.
plus by B.
Yeah, it's the quantified variable is the one that gets replaced, right?
Obviously.
Okay, so, yeah, obviously. X replaced by v, okay? And then this equals by textual substitution, Kale?
V is an element of X.
Yes.
Oh, we're done.
And that's what we proved this, right?
Proved.
Well,
So that-
but we just proved the 9.8 lemma.
Does that lemma prove that S is?
Well, we're not done yet.
Pretty much.
No, hold on. We're not done yet. We still have to do part 2.
We're not done yet.
Are you with me? We still have to do part 2.
And this is going to be really short.
Well, I think,
Two steps.
yeah. Okay, so now let's do proof of 11.5 part 2. Proof of 11.5 part 2.
I think you said 2.
Yeah, 2 and Joe.
Oh, that's great.
1, 2, 3. Okay? And now what is it? And now this is it directly, right? So what we're going to say, well, the thing that we're trying to prove is we're trying to prove this 11.5, right? So let's just start with 11.5. So we say S equals set over X, range X is an element S, body X, right? And now, of course, what we use now is 11.4, right?
Sure.
Okay? So this is 11.4. Okay, so Josh, it's your turn. So by 11.4, what is this?
Oh, wow. It's a-
Yeah, what is this? Okay, so now, well, yeah, we have to do it. This is the proof. Okay, so what is, so S equals this. By 11.4, what does that say?
Okay, for all X,
Okay.
range true,
For all X, range true,
X is an element of S.
X is an element of S
Equals X is an element of set over
is-
X.
of the set over X.
Range, X
Range,
is an element of S.
X is an element of S.
Body, X.
Body X.
That's it. Boom, boom. Translate.
Close set,
Close.
close for all.
Okay.
Are we good?
That
Gross.
ugly.
Yeah?
Gross. Oh. I get it.
I'm guessing we're using the lemma.
We're using a lemma.
Yeah, but what does the lemma say?
That
It
looks
says that
The lemma says that for in any arbitrary X, it doesn't matter what it is. Okay, so this equal, because we said we were going to do the lemma first.
that
So,
equals true.
so this equals by the 9.8 lemma,
For all X range true, body true.
yes, for all X, range true, body true.
I don't know what that is.
Wait, did I do, wait. For all X,
That's not even for all X.
oh, wait.
That is nifty.
Actually, you know what?
Range true, body.
I don't like, hold on. I don't like X here.
You want a dummy?
Let me rewrite
Let's
this.
dummy rename it.
Yeah, let's,
Oh,
Here.
don't do that.
yeah, here. Let's do 11 point, this equals by 11.4, only let's not call it X, let's call it
Do you want to
V, V,
Do you want to change the dummy for the for all or the dummy?
the dummy for the for all.
Okay.
So let's make it for all V. right? Just because we used V over here. Or did we use V or
We
did we?
did,
Yeah.
it's the other way around, so it'd make it confusing.
Let's
Yeah.
use.
No. This would make it, this will make it not confusing.
This will make it perfect.
Okay, so let's say for all, so what would this be? For all V, what?
Range true,
Range true,
V is of S.
V is an element of S, equivales, V is an, because see, before we had an X here and an X here, and those were different X's. Are you with me?
Yes.
Because this X was free and this X was bound, so that was confusing.
Yeah.
Okay, so let's have this, V is an element of X, range X is an element of S, body X. And now let's do
Lemma.
the 9.8 lemma.
That just makes it true, right?
Yeah. Because we know that for any arbitrary V, V is an element of S, equivals V is an, because we started off for an arbitrary element. So that means that for all of them it's true. Are you with me? That's why we say let V be an arbitrary element.
Alright, what is that whole arbitrary?
It's for all of them. It's for any of them. For all of them. An arbitrary. You see what I'm?
For any element?
Yeah, because it has this. We want it to be for an arbitrary element, so that for all of the V's that's true. Are you with me?
Right, so V is an element of one thing equals V is an element of another thing. So how? No.
No,
Oh,
not
right.
specifically
It's
anything.
specifically that thing.
Yeah. Okay.
Okay.
So what is this? So that by the 9.8 lemma, this is for all V range true. What? True. Yeah?
Equals,
But now equals by what? Equals by what? Equals by what? 9.8. Equals by 9.8. True. Boom. And we started with this and we got it to true. Are you with me?
that is wild. Is there another way of doing it?
Well, now watch this. Do you agree then that as long as we can prove the 9.8 lemma like we did, suppose we wanted to prove a different theorem, and one set is equal to another set, and suppose we said, okay, let's let V be an arbitrary element, and let's prove that V is an element of the first set, equals V is an element of the second set, and suppose we were able to do that. Do you agree that when we come over here, this part of the proof would be what?
The same.
Exactly the same.
Right.
Are you with me? And suppose we wanted to prove a third theorem, and then we had some set equals some other set. And suppose we said, okay, let's do the lemma, the 9.8 lemma. And suppose we said, let V be an arbitrary element, and we showed that V is an element of the first set, equals V is an element of the second set. And if we want, and then what would we do? After we proved that this lemma, what would we do? We'd come over here, and for that one, this would be the same. Well, look, if this is going to be the same every time, why should I make you write it out every time? We've done it once.
I agree. That's not.
Do you see what I'm saying?
So we just say the 9.8 lemma and be done.
So what we'll do is, this will be our proof technique. This will be a new proof technique that lets us shortcut not having to do this.
Just prove that there is an element that's in both of them.
Just prove the 9.8 lemma. We'll just say proof by 9.8 lemma. But we know, but see, we will,
have to do that.
because it would be the same thing every time.
Proves 11.5, that's it.
This will be our proof technique.
No matter what our two sets
So
are.
you
those
can-
steps-
No matter what the two sets are,
Like if you're trying to prove the two sets are equal, you can prove that two arbitrary elements
Elements.
are both an element of.
well, no, for one arbitrary element V, you show that V
Yeah,
is an
you
element of the
show that
first set,
element is the
equivals V is an element of the second
Okay.
set. And once you get that, why have to repeat this every time? Are you with me?
That's
I mean, wouldn't that be nice? I mean, don't you like this shortcut?
I like being lazy.
Yeah. But you could do this if you wanted. But this would be, actually, here's another thing. Do you agree that, if we could have done it without a lemma at all, right? If we had done it without using the lemma at all, what would we have done? We could have started with this. We could have gotten it to this, right?
And then
And then at this point, we could have gone over there
gonna be.
and brought all this stuff down for all v range true, da da da, for all v, and all of this stuff would have been wrapped up in for all v, for all v, for all v, for all v, for all. Are you with me? Well, actually, with this we would have had to do it this way. Instead of starting with one side, get to the other, we'd have to start with the whole thing. Are you with me?
Could we, in the middle of that proof, say, okay, now we're going to prove this part by getting one side to the other?
Well, no. See, you'd have to. Yeah, no, yeah, you couldn't do that. Yeah, you couldn't start with one side and get to the other. So you'd have to do it. You'd have to use the style of proof where you do both sides and you bring it down, you bring it down, you bring it down, and then you'd bring it down, and you'd get.
V is an element of S equals V.
V is an element of S. That would be true, and then this would be true, and blah blah blah. Right?
It'd be gross.
It would be gross. It'd be ugly. But I mean, it would be valid. It would be mathematically valid. So so does everybody understand that this is the basis now, this proof of 11.5 is the basis of a new proof technique?
Yep.
And basically what it says is that it's this. So let's write it out.
By the way, the math people really don't like this notation. Proving two sets in math are equal.
Well, no. In math, actually, the math people, this is the standard way to prove it, mathematical proofs. They just don't go back to this 9.8 lemma thing. The way mathematicians typically prove things is they just start off right here, but they don't have the predicate calculus machinery behind it. I mean, they don't usually show the predicate calculus machinery behind it as to why this is. Okay, but so anyway, so here's our proof technique. Proof technique to show.
So in other words, we're better than
I didn't say that, but to show S equals T, let V be an arbitrary element. Let V be an arbitrary element. And so you have to say that. You have to say, in there you have to say, let V be an arbitrary element. And prove what we're going to call the 9.8 lemma. So to show that this equals this, we will prove the 9.8 lemma. Show that V is an element of S equivales V is an element of T. Are you with me? Sports fans? Huh? So here it is. This is so important we're going to put a big box around it. And unfortunately, our author does not, state it like this and put a box around it. But it's so important, and this technique is just, we'll use this from now on. I mean, a lot. So this is basically a way of, because you really are using, basically what you're doing is you really are using 11.4, but you're using 11.4 with 9.3, So that's why we're going to call, sorry, not 9.3, 9.8. So we're going to call this proving the 9.8 lemma, okay? So, all right, so from now on you can omit the actually, to recap, from now on you can eliminate part 2. From now on, forevermore, you may omit part 2. Okay, because it's the same, part 2, because it would be the same for each proof. Because it would be the same for each proof. Okay?
Yeah.
Yeah? Pretty sweet, don't you think? All right. Let's go on. Okay, so here is the 11.5.1 is an abbreviation. Okay, and here we want to use this abbreviation because this abbreviation is the standard way they do it in math, in traditional math notation. Okay. So 11.5.1, it's actually just called abbreviation. And what it says is that, oh, you can read it there. What it says is that for a single variable, now, so what's missing in that 11.5.1 on the left? The body's missing, right? So do you remember how we had an abbreviation? If the range is missing in a quantification, what is that an abbreviation for? Range true. Well, if the body is missing in a set comprehension, no, it's not empty. It's what? What's the body?
Universal.
No, what's the body? Look on the right side of 11.5.1.
It's the dummy.
Yeah, it's x. It's the dummy variable. It's the variable itself.
Sure.
Are you with me? Is everybody clear on that? Yeah? Okay, so that's an abbreviation. Okay.
Now, do we still say body X, range R, or dummy X, range R, body X, or do we still
Well, you could either say body x or
just say dummy X, range R?
yeah. Okay. So just to give you some examples, traditional math. And that is the traditional way to do it. It's x, set over x, range R. Whereas with formal methods, we have this extra body in range, set over x, range R, body x. Okay? And here's an example. So tell me, what is this? The set over I, range 0 less than I less than 4. What is that set if you were to enumerate it all out? See, what would this be if you enumerated it all out?
1, 2, 3.
Yeah.
Yeah, the set 1, 2, and 3. Yeah? Are we good?
Yep.
And that's the same as set over I, 0 less than I less than 4, body I. Okay?
So how would you perform operations on that?
Yeah, see, what you should do is if you ever have a set like this and you want to do some theorems, just use 11.5.1 to stick that in there, and then you can proceed.
Could you change your range so it's like this and something else?
Well, this can be any Boolean expression, but it has to be type Boolean, and it's all the i's for which this is true that satisfy. And you could have ands and ors in here. Is that what your question was?
No, because you say you want to say, because you know how, like, say you want to have the body as like 2 times I. So
Yeah, well, you can't. Yeah, if you want to have it 2 times I, then you got to use
Right.
this. Yeah.
No, but couldn't you change your range so it's even?
Oh yes, I imagine. Yeah. Okay, I imagine that no
You
matter.
can do an abbreviated version. Yeah.
I imagine that I imagine that for any set that you can think of that has something in here other than x, you could probably figure out a way to change the range to have an equivalent set be done this way. Is that what you're saying? Yeah. I hadn't thought about that, if that's always possible, but it seems like it. I bet it is. I bet it's always
I'm sure
possible.
it is, yeah.
Yeah. Okay.
Especially with trading.
What about trading?
To be able to take the body and put it in the range.
Right. Yes. Oh, that's true. Yeah, you could trade. Yeah, actually, that's a good point.
So that would
Yeah. In fact, that's a recipe for how you would do it. You would do it here. You would trade, and then yeah. Well, but trading, exists. Well, yeah, I'd have to think about that. All right. So now let's take a look at 11.6. 11.6.
Don't cut that.
Okay, so 11.6 says relates traditional math notation to formal methods math notation, because look, what do we have on the right side of 11.6? Oh, maybe this is exactly what we just said. Is it not? Ho ho! Look at the right side of 11 point, look at the left side of 11.6. What is the left side of 11.6? It's a set using what? Some arbitrary range and what else?
An arbitrary body.
Some arbitrary body, E, which could be like x squared or whatever, right?
Yeah.
And what that's saying is that equals
Set over Y.
the set over Y
Body, or range.
with just a range. So that's the traditional math way of doing
Range
it.
has a body.
But the range is there exists an X range R body Y equals E.
Yep.
So actually, that's funny. We were talking about that. Is there a way to do it? Da 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 da. And 11.6 exactly shows us how to do it.
We have the same thought process.
Yeah. Ooh. So which means that was a really good thought process. Yeah.
Is there a body Y?
No. On the right-hand side of 11.6, there's no body. Are you with
There's
me?
a body within the there exists, but not within the set.
On the right-hand side of 11.6, the existential expression, there exists an X,
Yes.
range R, body Y equals E, that whole thing is this range right here.
But by 11.
That whole thing is this range right here.
Right. But by 11.5.1, is the body understood to be X?
Yes. Oh, no, I'm sorry. In that case, it would be Y. In that case, it would be Y. Yeah, oh, yeah. In that case, the body is understood to be Y.
Now, is the Y bound in every instance there?
Yes.
It's bound within the X.
Yes, because Y is free in there exists an X.
Okay.
So it's bound to the Y of the set dummy variable Y. Oh, that was a great discussion because I mean, we said, well, why? Is there a possible? And then, sure enough, 11.6 shows how traditional math notation relates to formal methods notation. So 11.6 relates formal method notation to math notation.
Y doesn't exist in any of them.
Yeah, in all of these, you're assuming that.
You just have to pick a new variable.
Right.
It's not in-
Right. Actually, let's do a few examples of this.
What's math notation? Is that the stuff on the left?
Traditional math.
No, the traditional math notation is just
Omitting the.
is omitting the body. Okay, so here let's do an example. Let's do some examples. So suppose you have this set. The set on X, range 0 less than X less than 4, body X squared. Okay? By 11.6, what is? This is
Set over Y.
same as set over Y,
Range, there exists an X.
range, there exists an X,
Body.
Range.
Oh yeah, sorry. No, yeah, range.
range,
0 is less than X is less than 4.
0, good, very good, 0, less than X, less than 4,
Body.
body,
Y equals X squared.
Y equals X squared. Boom, boom. Are you with me? And in fact, if we enumerate this,
Let me guess, we get 1, 4, and 9.
yes, 1, 4, and 9.
I enumerated the top one.
See? Does everybody see that 1, 4, 9, it's the set of all Y such that there exists an X between 0 and 4,
Wait,
body Y equals X squared.
So that
Is that right?
the X would be 1, 2, and 3. So X squared would be 1, 4, and 9, which is the Y. And then it returns to Y.
Yes, and there exists a Y, and it's the Y.
9.
And it's the Y, which is the 1, 4, and the 9.
Because the body is understood.
Yes. So see how much contortion you'd have to go through if you don't have the body? That's the kind of contortion you'd have to go through to do set comprehension.
Shouldn't there be a for all X?
No?
It says there exists.
No, I think no, there exists. Think about it. The range is there exists an X such that x squared equals y.
So it's going to be 1 or 4 or 9.
It's the set of all the y's.
So go ahead and like, I guess solve that exists.
What do you mean solve
Like the
it?
range. Like, I mean like enumerate the range kind of.
1, 2, 3.
So like, right.
Yeah, right. Yeah, the possible values for x are 1, 2, and 3.
And then that there exists would be 1, 2, and 3, but squared. So it'd be 1, 4, and 9. And that'd be the range of the original set. So
Yeah, it's the set of all y's.
It's to be set over y, 1, or range 1 or 4 or 9, right?
Does that mean we get y equals x, y equals 1 squared, or y equals 2 squared, or y equals 3 squared?
Doesn't the set just 1 set with element 1 in it? Doesn't that satisfy that though?
No, because it is the set over all y in this range,
Which are 1, 4, and 9.
which are 1, 4, and 9. Okay? Oh, that was a good one. Okay, so let's go to the next one, 11.7.
So what would the difference be if we used for all instead of there?
Well, let's not go there. I don't want to investigate that at the moment. Okay, so now the next topic is sets and predicates. Sets and predicates. Now, 11.7, this is 11.7. Okay, so now actually you're going to prove this in the homework. 11.7 is a theorem proved in the homework.
We have homework due. We got it.
Unfortunately, you have homework the Monday you get back from Thanksgiving.
It's not bad though.
Oh, good. Have you already done
I
it?
did it during my econ class yesterday.
You did it during your econ class. I feel sorry for your econ class, professor. I hate it when students do homework for other classes when they're sitting in my, anyway, whatever. Okay, 11.7 is a theorem. Hey, watch out. We don't need to talk about other classes. Okay, 11.7 is a theorem proved in the homework. Okay. Oh, by the way, let's take a look at 11.6. Does everybody see why that's equals instead of equivalents in 11.6?
Yeah.
Because what are you talking about? Equality between sets. But whereas 11.7, it's a Boolean, so that's equivalents. Are you with me? So X is an element of this set, equivalents this R. Okay?
Yeah.
Okay?
It's kind of a lengthy proof.
All right. Now here's the thing that's confusing about 11.7, which is why I have 11.7.1 in our equation sheet. 11.7 is a little confusing. Let's write it down. It's, look, X is an element of the set over X, range R, and now we're using, without the body, equivalents R. Okay? Now here's what's kind of confusing about this. Let me ask you this. Is this X bound or free?
Free.
And suppose this R is an expression and it has X in it. Would the X in this R be bound or free? That would be free. But what about the X that is in this R? Right, okay. So this X is free. This any X in this R, any X in this R is free, but what about any X in this R?
Bound.
So whenever you read this, you have to be aware of that. Now let me give you an example of this. Like I say, the proof's a homework problem, but let me give you an example. Because look, isn't it interesting? you have this x as an element of some set, and that equivales the range. But what is the range? It's a Boolean expression, right? Okay, so suppose the example is this. Suppose R is this expression 0 less than or equal to x less than 5, right? So now, what is this? X range R. So what would that equal? That would equal x, the set x, range 0 less than or equal to x less than 5. And we're going to use the conjunctive meaning of equals here. And so what elements would that be?
0, 1, 2, 3, 4.
0, 1, 2, 3, 4. Right? So what does it mean for x to be an element of the set? Oh, sorry. Yeah, that's right. What does it mean for x to be an element of the set over x, 0 less than or equal to x less than 5? What does that equivale? What does this equivale?
It equivales the range.
Which is what?
0.
This equivales 0 less than or equal to x less than 5.
Yeah.
Because this is true or false,
If
depending on whether this is true or false.
if x is part of that range, then it would be true, and if it's not part of that range, then it'd be false anyway. So it depends on the range.
Yeah, in fact, it is the range. I mean, in fact, this expression is the range. That's what that's telling you. That's what that's telling us. Yeah? Does everybody see how that worked?
Yeah.
So then what's 7.1?
Well, 11.7.1 is with,
Oh, it's just changing.
it's changing the, yeah.
It makes sense once you've done the first part.
Yeah.
You guys like, oh.
All right. You guys have a great Thanksgiving.
Yeah, you too.
See you next time.
Happy turkeys, people.